You can see in this example that our movable pulley is attached by a light inextensible string to two masses. Now it's not too difficult to see how this system will move. The 2 kilogram mass will move up, and so will the 1 kilogram mass, because they are much lighter than the 20 kilogram pulley. Okay, let's consider the accelerations of these masses. So to see what's going on, let's suppose that the 2 kilogram mass moves up a distance of 1 meter. Let's also say that the 1 kilogram mass moves up a distance of 2 meters. So the question is, how many meters of string are fed into the center of the system? Well, we have 2 meters from the 1 kilogram mass fed in, and we have 1 meter from the 2 kilogram mass fed in. So in total we have 3 meters of string fed into the center of the system. Okay, so this pulley has moved down a certain amount. Well, it hasn't actually moved down 3 meters. 3 meters worth of string have been fed in. So that means that if we add this length of string onto this length, the answer is going to be 3. And that 3 is divided by 2, as you can see. So we have 1.5 meters of string on either side. So what we do is we add the distances travelled by the 2 outer masses and divide by 2. So we are taking the mean distance travelled by the 2 outer masses. So let's suppose that the distance travelled by the 1 meter mass is s sub 1, and the distance travelled by the 2 meter mass is s sub 2. Well, the distance travelled by the 20 kilogram mass is going to be S1 plus S2 divided by 2. So we just get the mean distance. So now if we differentiate this expression, if we differentiate the distance with respect to time, we get the velocity of the 20 kilogram mass. And you know, we just we have a half times the derivative of S1, so we have half the velocity of the 1 kilogram mass plus half the velocity of the 2 kilogram mass, or we can write that as V1 plus V2 divided by 2. So the velocity of the 20 kilogram mass is the mean of the velocities of the 2 outer masses. And of course, in a similar way, we can differentiate again and show that the acceleration of the 20 kilogram mass is the mean of the accelerations of the 2 outer masses. And of course, this is what we need when calculating the resultant forces on the masses. The accelerations are constant. That's because the resultant force on each of the 3 masses is constant. However, the velocities are not constant, of course. The velocities are changing. But at any instant, the velocity of the 20 kilogram pulley is the mean of the 2 outer, the mean velocity of the 2 outer masses, and the same goes for the distances travelled. Okay, so let's call the acceleration of the 1 kilogram mass A, and we can see quite clearly that 1 is going to accelerate up. It's so much lighter than the middle mass, so it looks like it will accelerate upwards. And as for the 2 kilogram mass, it's quite clear that that's also going to accelerate upwards, but we have no reason to suppose that the 2 kilogram mass has the same acceleration as the 1 kilogram mass. As a matter of fact, in general they don't, unless of course they both have the same mass. So we'll call the acceleration of the 2 kilogram mass B. So now we know that the magnitude of the acceleration of the 20 kilogram mass is just got by adding these two and dividing by 2. We just take the mean of the accelerations. Okay, so here are the forces. So we have a light string, its mass is essentially 0, so we've shown before that that means that the tension is the same throughout the string. So the upwards forces on these masses due to each string has the same magnitude T. Let's get the resultant force on the 1 kilogram mass. So we will take upwards as positive for the 1 kilogram mass, since we know that it's going to accelerate upwards. So that resultant force is T minus 1g, and by Newton's second law that's the mass by the acceleration, which is A. Now let's look at the force on the 2 kilogram mass. Well, upwards is positive for that. It's going to accelerate upwards, so it's T minus 2g equals its mass, which is 2, times its acceleration, which is B. Now for the 20 kilogram mass, now that's accelerating downwards, so we take downwards as positive. So it's 20g downwards minus the upwards forces on it, which are 2t, and it's equal to its mass, which is 20, times its acceleration, which is the mean of the accelerations of the outer masses. So you can see we have 3 equations and 3 unknowns. What I will do is plug in for A and B into the third equation, so we'll get an equation in T only. Alright, so on the right hand side we have 10 into A plus B, where A is T minus 1g, and what's B? Well, we get B from the second equation. It's a half T minus g. Okay, so we solve for T, and if we go back here we can see that that makes sense. So T is 2.35 g. It makes sense in terms of the direction of the acceleration of each mass. So the upwards force 2.35 g is greater than 1 g, so 1 kilogram mass accelerates upwards. What about these two? Well, if 2 times 2.35 is 4.7, so we have 4.7 g up, but we have 20 g down, so that makes sense. And here we have 2.35 g up, which is greater than the 2 g down. Okay, so now we can calculate A. So the resultant force on this mass is T minus g, which is 1 times A. So we have 2.35 g for T minus 1 g. That's 1.35 g. So that's A. So you can see that that came out to be positive, so that makes sense. That's exactly what we expected. Okay, that the 1 kilogram mass would move in the positive direction, which is upwards for that mass. Next we can get B, so that's this equation here. Half of T is 1.18 g, and again this comes out to be positive just as we expected. So the 2 kilogram mass does indeed move in the positive direction, which is upwards. Finally, we take the mean of the accelerations, we add the accelerations and divide by 2, and that gives us the acceleration of the 20 kilogram pulley. And the downwards direction, remember, is positive for the 20 kilogram pulley, and this obviously comes out to be positive since A and B are both positive. Now let's look at the general situation. So the masses are M1, M3 and M2. Since these masses can obviously be anything we like, we do not know how the system will move. But to keep things simple, we will assume that the system could move like this, where the 2 outer masses both move up, but the middle mass moves down. Or we could reverse that, have the 2 outer masses moving down and the middle mass moving up. So one of those 2 situations we will consider. There may be other possibilities. It's possible that this one could move up while both of these could move down. Now, I'm not sure about that yet, but I won't assume that for now. Also, we could have this one moving up and these 2 moving down. I'm not sure if that can happen either. But what I am certain of is that we cannot have this situation. We cannot have the 3 masses moving up, obviously. And neither can we have all 3 of them moving down, because then the string would have to stretch, of course, for that scenario, so that's impossible. Okay, so let's assume that M1 moves down with acceleration A, M2 moves down with acceleration B, and M3 will move up with acceleration A plus B over 2. Okay, we saw that previously. The acceleration of the middle mass is the mean of the accelerations of the outer 2, although I've reversed the accelerations for this example. In this case we are removing string from the center of the system. Okay, so like before, all the tension forces are the same. So let's get the force on M1. Well, downwards is positive for M1, that's the direction of the acceleration, so the resultant force is M1g minus T equals M1a, As for the force on M2, I'll call it F2. Downwards is positive, so it's M2G minus T equals M2 times A. And finally the force on M3, we take upwards to be positive. Its acceleration we are saying is upwards. So it's 2T up minus M3G down equals its mass, which is M3, times its acceleration, which is A, plus B over 2. Okay, so like before, we make A and B the subject of the first two equations, and we plug those, what we get, into the third equation, and we just get an equation in T only. So we have to get half of A, that's half of this here, that's what we have, first two terms here, plus half of B, so half of this thing here, second two terms. Bring all the terms involving T to the left hand side. So we're going to get plus a half M3T over M1. And this is going to be M3 times a half T over M2. It's going to become plus a half M3 T over M2. So those are the terms involving T. Bring them to the left hand side. And bring this term, which doesn't involve T, to the right hand side. So we have half G plus a half G is 1 GM3 plus another GM3. That's 2 GM3. Now, to get rid of the 2 in the halves, you can multiply everything by 2. And to get rid of the denominators M1 and M2, multiply everything by M1 times M2. So the first term becomes 4 M1 M2. Oh yeah, I just want to take T out of this. 4 M1 M2. 2 times a half is 1. One of the M1s cancel, so you get M2 M3. For this term, the M2 cancels, and you're left with M1 times M3. Okay, and on the right hand side we have 2 M1 M2 times 2 M3G. It's 4 M1 M2 M3 times G. Okay, so there's a formula for the tension. As an aside, let's look at the accelerations. So we go back up here and we can see what A and B are. Okay, so we can plug in for T and get a common denominator. So I want to get this thing into a single fraction. So we have a like term here, 1m2 m3g and minus 4m2 m3g. Okay, so this is A. Now I've written down B. So this time we're dividing T by m2 instead of by m1. So m2 disappears out of the numerator here. You can see that this example has the same form as the previous example. We have to get the tension in the string, so you could go through it just like the previous example, or we can use the formula that we derived and plug all the values in. Now M3 stands for the middle mass, the mass of the movable pulley. M1 and M2 are the two outer masses. So M3 is equal to M, and this is what we get, so we can simplify this. Okay, in part 3, M is given a value of 9.6 kilograms. With that value of M, the tension is 4.8 G newtons. So we have the tension. Okay, so here's the picture. Let's look at pulley B. Well, the tension force is 4.8 G, and if we double that, we get 9.6 G. So the force on B up is 9.6 G, but the force on B down is 9.6 G. So the resultant force on pulley B is 0. So that means that pulley B remains at rest. You know, by Newton's second law, this is mass times acceleration. But if it's 0, then the acceleration is 0. So if it starts at rest, it remains at rest. You can clearly see that the resultant force on the 4 kilogram mass is 0.8 G upwards. So the acceleration is got by Newton's second law. So 4 times the acceleration of the 4 kilogram mass. So there's the acceleration, and it's upwards. We can see the resultant force on the 6 kilogram mass is 6 minus 4.8, or 1.2 g in the downwards direction. So this mass will accelerate down. So the magnitude of the acceleration of the 6 kilogram mass is 0.2 g downwards. So this thing is remaining at rest. So that means the string is moving up along around pulley A, it's gliding in under pulley B around C, and the string is moving down on the right hand side. You've got to imagine pulley B just sitting here at rest, and it's not rotating either because it's a perfectly smooth pulley, so the string is exerting no force on it in the direction along the string. The string is just gliding in underneath pulley B while pulley B remains at rest. Okay, this example is quite similar to previous examples, except at this time one of the masses lies on a horizontal surface. Well, it's a table and it's perfectly smooth, so the resultant force on this mass is due to the string. The vertical forces cancel out and there's no friction force. So I'm calling the force on the mass due to the string T, and we're just dealing with one continuous piece of string, so the string tension is the same throughout this string. So the resultant force on mass M1 is M1 times its acceleration. So actually for mass M1 it can only accelerate to the right. It certainly can't move to the left because the string cannot exert a force on M1. It cannot push on M1, it can only pull on M1. Okay, let's take this mass here. I'm assuming that it's accelerating upwards. We don't know the direction of its acceleration because we don't know the mass of this pulley here, so we have no idea how the system will move. So we'll assume that the 1 kilogram mass moves up. So, we can see that string is being fed onto this movable pulley from both sides of the system. So if we know the accelerations of the two outer masses, then the pulley acceleration is the mean of those two outer accelerations. So let's take downwards as positive for the movable pulley. So the resultant force is m2g minus 2t. By Newton's second law, that's the mass, which is m2 times the acceleration, a plus b over 2. We can take upwards to be positive for the 1 kilogram mass, so we're saying the direction of acceleration is upwards. So the resultant force is t minus g, and that's equal to 1 times the acceleration b. Similar to previous examples, to get the tension, we take this equation here and sub in for A and B from the other two equations. Now I'm multiplying this equation by 2 to get rid of this 2 in the denominator. So on the right hand side we'll have m2 times A plus B. Well, A comes from this first equation, that's T over m1. B comes from this equation down here, that's T minus G. Now I'll take terms that do not involve t to the left hand side, so that's 2m2g, and the minus m2g on the right hand side is brought over. Terms that do involve t are brought to the right hand side, so this will become plus 4t, and we have m2 over m1 times t plus m2 times t. Okay, so factorizing t out of this, we're left with 4 plus m2 over m1 plus m2. That's divided into the left hand side, which is 3m2g. Now you could multiply above and below by m1 if you like. So now we have an expression for the tension. So if we know the masses of both of these particles, we can get the tension force, and from the tension force we can get the accelerations. Okay, next we're going to look at the condition for the pulley to be at rest. Well, if the pulley is at rest, the upwards forces on the pulley must equal the downwards forces. Well, the upwards forces are 2t. Okay, so the upwards force is twice this. So that's 6 m2 m1g over this denominator, and it must equal the downwards force, which is the weight of the pulley. That's its mass m2 times g. Alright, so we can divide both sides by m2g and multiply both sides by this denominator. To get this here, 6 minus 4 gives us 2m1 on the left hand side. Now, the condition for the pulley to be at rest is this expression here, or equation. So how would we get this? Well, we could just divide both sides of this thing by m1, m2. Okay, so we'll get to something of the form of the left hand side here. Okay, we choose m1, m2 because we just want to have numbers on top, just like we have here. Okay, so we just get a 2 on top here. We get 2 over m2, as we see here. And this fraction is 1, so you can see what we get. We get 2 over m2 equals 1 over m1 plus 1, or 2 over m2 minus 1 over m1 equals 1. So the pulley C will remain at rest if this quantity here is equal to 1. So that number k must be 1. Now in this example it's clear that both of these masses can only accelerate towards the center of the system. So the string only pulls, it cannot push. So let A and B be the accelerations of these two masses. Well, we know that if that's the case, then the pulley here has an acceleration whose mean is the acceleration of the the acceleration of the pulley is the mean of the accelerations of the two masses, and it's going to have to be downwards. So if the movable pulley accelerates at all, it has to be downwards. Now we're dealing with just one piece of string. The string tension is the same throughout. Let's say that string tension is T. Let's look at the other forces on this mass. Well, we have the weight of this mass, mg, and it's resting on a horizontal surface. So the force on this mass due to the surface must also be mg up, because the mass is not accelerating in the vertical direction. So we need to indicate these vertical forces because friction comes into this problem. Okay, if this mass moves at all, it must move to the right. If it's on the verge of moving, or if it's already moving, the maximum friction force is acting. And that maximum friction force is mu times the normal force on the mass. So it's mu times mg. Similarly over here, we know the direction of motion of this mass. If it's to move at all, it must move to the left. So the friction force opposes that motion. So it's mu times 2mg. Okay, we want the tension in the string. So let's look at the resultant force on this mass. Well, the vertical forces cancel out, and we'll take the direction of the acceleration to be the positive direction. So the resultant force is T minus mu mg. By Newton's second law, that's mass times acceleration. For the movable pulley, downwards is positive because that's the direction of the acceleration. So the resultant force is plus 4mg minus 2t. And by Newton's second law, that's mass times acceleration, which is a plus b over 2. Finally, the direction of the acceleration for the 2m mass is to the left. So the resultant force is T minus 2 mu mg, and that's mass times the acceleration. That's 2m times b is the acceleration. Okay, like before, we take this equation here and sub in for a and b, so we get an equation in t only. We want t in terms of m and mu. Alright, so I've multiplied this by 2 to get rid of this 2, and we need to get a plus b here. Well, we get a from this equation, divide all this by m. So a is t over m minus mu g, and as for b, well, b is t over 2m. We divide this by 2m to get mu minus mu g. So here's our formula for the tension. Okay, next we will look at the acceleration of this mass here. The resultant force on it is T minus mu mg. By Newton's second law, that's its mass times its acceleration. So we divide by m to get its acceleration. So we take t and divide by m. That knocks out the g on top. So we can write this mu g as 5 mu g over 5 to get a common denominator. So we get 4g minus mu g. So now we have a formula for the acceleration of that mass. Notice that the acceleration doesn't depend on m. It depends only on mu. And mu depends on the material that the mass is made of and the surface that m is in contact with. Now let's look at the resultant force on the 2m mass. Well, that's T minus 2 mu mg, and that's equal to its mass, which is 2m, by its acceleration, which is b. Okay, so we divide it across by 2m to get b, so we have to divide t by 2m, so on top here we will be left with 2g into 1 plus mu all over 5, and we subtract mu g. Well, that's mu g can be written as 5 mu g over 5. Get a common denominator of 5. So on top we're going to get a 2g plus 2g mu minus 5 mu g. So that's minus 3 mu g. And we can take that g out. So we have a 2g here, so we need a 2 here. Okay, so now we want a relationship between A and B. Well, in the question, the acceleration of the m kilogram mass is referred to as F. Of course, that's just a label, but okay, I'll change it to F. Little f is sometimes used as a notation for the acceleration of an object. The reason why little f is often used is because big F is the resultant force. So the resultant force by Newton's second law is the mass times the acceleration. So the little f reminds us that we're referring, that's related to the resultant force. That's a possible explanation for why little f is used. Anyway, so how do we write this thing here, B, in terms of F? One systematic way to do that thing is to make mu the subject of this equation here, because mu is the variable, G is fixed, and if we get mu in terms of F from this equation, and we just plug in for mu here, that means we are left with B, the acceleration of the 2m mass, in terms of F. Okay, so if we do all that, we have the acceleration of the 2m mass in terms of F. The G is just a constant. Now, as a brief aside, I just want to mention why we are given this inequality here. Why is mu less than 2/3? Well, let's look at the resultant force on the pulley. It's 4mg down minus 2t up, so minus twice this up. Now we know from the setup that the pulley has to move down. It can't move up because the strings cannot push on the two masses. So this force must be positive. Okay, in other words, the 4mg, the weight of the pulley, must be greater than the 2t pulling up on the pulley. Alright, so downwards is positive here. Well, of course, the resultant force could also be 0. That's a possibility, in which case the pulley doesn't move at all. Okay, so solving this inequality leads us to mu less than or equal to 3/2. But mu is normally a number between 0 and 1. So it's always going to be less than or equal to 3/2. So this isn't very useful. Okay, we could then look at the force on the mass whose mass is m. That's the mass on the left side. Here's the resultant force. We fill in for t. We want this force to be greater than or equal to 0. It can never be negative, because if it was negative, it would mean that this mass would move to the left, and that's impossible. If we solve this inequality, we get this statement, but this is always true, because mu is usually less than 1, so this isn't helpful. Okay, finally we have the 2m mass. Get the resultant force, we want it to be positive, because if it's positive means that the 2m mass is moving to the left. It's the positive direction for the 2m mass. It cannot move to the right. So it must be positive, or it could be 0. In that case, it doesn't move. Okay, so it boils down to this. Multiply everything by 5. So bringing the 4 over and changing signs switches the direction of this. You'll end up getting mu less than or equal to 4/6, which is 2/3. So to get a meaningful result for the 2m mass, that is for the 2m mass to move to the left or not move at all, in that case the resultant force is equal to 0, we must have that the coefficient of friction is 2/3. If it's greater than 2/3, then the 2m mass actually moves to the right, which is impossible, of course.